Yeah, hello everyone and welcome to my talk. First of all, I thank the organizers for giving me this opportunity to present my work related to the benign termination of relativistic electron beams in tokamak plasmas. So to start with, as an introduction for those who are not used to fusion plasmas, as you have seen from the previous talk, so in a tokamak plasma, you have both a toroidal magnetic field that comes from the blue-colored field coils that you see here, as well as a poloidal field that comes from the plasma current that is driven within the plasma toroidally. So ideally, in a normal state of operation, everything must be stable and things should work fine and we should be able to produce fusion energy from such a setup. But unfortunately, there are several issues that tokamak plasmas face. So one such burning issue is known as the disruptions. So what are these disruptions? So a disruption is a sudden termination of the plasma discharge due to large-scale instabilities. So this means sometimes in a normal operation you can have large instabilities in the plasma which can actually grow and it can lead to stochastization of the magnetic field. So when such stochastization happens, then the magnetic field is ergodic and you can have fast loss of thermal energy from the plasma. So this means that in such situations, the plasma can lose majority of its thermal energy in a very short time scale. So what you typically see in an experiment like this is that, as you can see in the picture there, the temperature is dropping within a millisecond or so from what is supposed to be the normal operation. So what's the result of this? This means all the thermal energy of the plasma is dumped within a short region near the diverter, and it can lead to massive heat loads. So this is a detrimental effect that needs to be avoided. And apart from this massive heat loads, we also will have a decay in the plasma current. So if you know that in a plasma, the resistivity scales to the power of T power 3/2. So this means if the temperature drops by a factor of 100, the resistivity increases by a factor of 1000. So this means due to large resistivity, the plasma current starts to drop. So typically in our tokamaks, the drop of the plasma current happens over a time scale of a few tens of milliseconds. So the impact of this drop in plasma current is that since the magnetic field is changing very fast, so the vessels or the structures that surround the plasma will have currents induced in them, and they will cross with the existing magnetic field and develop very large forces. So that is also a detrimental effect. And finally, we would also have something called as relativistic electrons that gets generated when such a disruption occurs. So these disruptions are not that they'll keep happening all the time. In a proper machine, they will happen once in a while, but still that has to be avoided. So we'll see why it is so dangerous. So what are these relativistic electrons? So this is my focus, and these relativistic electrons are basically electrons that travel at the speed of light, close to the speed of light, with energies of the order of few tens of mega electron volts. So where did these, first of all, these electrons form from? So as you have seen, when the plasma cools down, after a thermal quench, you have very large resistivity. That means that the electric field, parallel electric field, also becomes large. So such an electric field can actually accelerate a certain small population of electrons to relativistic velocities. So how can electrons move to relativistic velocities? That happens due to the fact that in a plasma, the collision frequency, let us take any electron, so the collision frequency scales in such a way that it strongly decays with the velocity of the electron. So this means for a given electric field on an electron, if the force, if the drag force is smaller than the force due to the electric field, then those electrons that are faster or have a certain minimum momentum, they will always keep on accelerating. That means the more they accelerate, the less frictional force that they face, and this means they will keep on accelerating to relativistic energies. So such electrons are known as relativistic electrons or runaway electrons. So now this happens only to a small population of the electrons in the plasma, but what is important is something called as avalanching. So this avalanching means that if you have a relativistic electron and it goes and hits a thermal electron, because the relativistic electron has far more momentum or energy than is apparent from its speed, which is speed of light, both of them after collision, both of them will become relativistic. That means there can be an exponential growth of runaway electrons, which is typically called as the avalanche mechanism. This means after the cooling down of the plasma, a small population of electrons became relativistic, and those are leading to an avalanche, and it leads to a full beam of relativistic electrons. So this is what you can see from the right-hand side picture. So you see that initially you had a certain plasma current, and as the plasma current decayed after the thermal quench, the relativistic current also increases, and eventually all the plasma current is carried by this relatively smaller population of relativistic electrons. So in typical tokamaks, if the plasma density is around 10 power 20 particles per meter cube, then relativistic particles density is of the order of 1,000 times lower, so of the order of 10 power 17 or so. Now the impact of all the current being carried by relativistic electrons is that they can be a significant risk to future fusion-grade tokamaks like ITER. So relativistic electrons are also seen in existing tokamak devices, but they have not really led to serious issues, so to say. But as you can see, since they are a big fraction of the total plasma current, when you have higher plasma current devices, you will have a lot of risk due to these electrons. So what is the risk associated? You can see that typically plasmas after a disruption are vertically unstable, and they go on either to the top side or the bottom side, but eventually they go and hit the wall. So that means such high energetic beam of relativistic electrons can go and in fact damage the wall. And for a nuclear device, it will take months or probably years to fix this and get the machine restarted. So we don't want outages in fusion-grade devices, so that is why this is a big issue. So, and what you see here in the picture is already in the machine called JET, or Joint European Torus. So here you can see the tiles are simply melted or evaporated due to the impact of these runaway electrons. So now what is the solution for this? So there are some possibilities for a benign termination. A benign termination means that you simply have a disruption, you generate runaway electrons, but in the end it does not lead to any damage to the walls. So how is it possible? So experimentalists have in fact in the recent years been successful in producing benign terminations in spite of having these runaway electrons. So typically what they do is after a runaway beam is formed, a large amount of material is injected in the form of massive gas or shattered pellets, typically deuterium or some impurity or like neon, and after these injections in certain scenarios they find that it leads to a benign termination. So also in terms of simulations, it has been shown in a few works with respect to the jet tokamak and the D3D tokamak that benign terminations can be initiated due to MHD instabilities of the runaway electron beam. So now the main question that comes up here is, can this be replicated in ITER? So because that is for ITER, in fact, runaway electrons are by far the most problematic issue. So you can even hear the big bosses of ITER sometimes saying that they have sleepless nights mainly because of the issue of runaway electrons, and there is no clear cure until now, though there are mitigation strategies for the same. So in ITER, for example, what we observe is that there is a natural tendency for the plasma to become unstable. For example, you can see in the picture on the right-hand side, so the full elongated plasma, when a disruption happens, Since the plasma is vertically unstable, it starts to go up or down. In this case, it is going up. This means the plasma is shrinking in size. So you know that the edge safety factor in a tokamak roughly scales as A square over IP. And since the plasma is shrinking, A is decreasing, the minor radius. So this means the Q95 is going to decrease. And also, one more thing, as you have seen that relativistic electrons will have not too much of a collision frequency, so they are not subjected to any resistive decay. That means you have a background plasma that is highly resistive, but current is carried by relativistic electrons that are not really seeing that resistance. So that is the uniqueness of this system. So you can then, that means that this Q95 will be unaffected by any of the, unaffected because of IP, because IP simply does not drop once relativistic electrons form. The current remains nearly constant, so to say. So the aim here then is to assess if we can use MHD instabilities to find benign termination scenarios in ITER, and can it really work or not. So for that, the physical model that is used is on the basis of the MHD, fusion MHD code called JOREC. So in this, what we do is that the runaway electrons are treated as a separate species or a fluid species that interacts with the background plasma MHD electromagnetically. So, and apart from that, there are different species, that is, impurity species are extremely important when it comes to relativistic electrons. So they affect how fast these electrons can grow due to avalanching, etc. So those impurity species, deuterium ions, neutrals, etc., also evolved and coupled to the other equations. So partially ionized impurities especially are important for runaway avalanche, the effects of which is also included. Now, not only the plasma is modeled here, but also the effect of exterior conducting structures, the passive structures, the vacuum vessel layers, etc. is also taken care of. This is taken care of by using what is called as this JOREC star wall. So what this really means is that the exterior is not really considered in terms of the simulation domain, but the effect of the exterior on the plasma is taken care by using the formalism of Green's functions. That is, you can relate normal magnetic field component to the tangential magnetic field component on the plasma boundary, which actually take care of what happens in the vacuum region, so that you avoid explicitly modeling the exterior. So that is what is referred to as JOREC star wall. So if, sorry for the huge sea of equations, but for those interested in the equations, so what goes on inside is basically a reduced MHD set of equations coupled to a runaway fluid. So here the magnetic field is expressed in such a way that the toroidal component does not change with time. So you have a stream function psi. The electric field is given with this potential F0 grad U. And the velocity of the background plasma is largely represented by the E cross B drift. So the equations that you have, if I have to go through quickly, are the uncurled Faraday's law here, the vorticity equation comes from the momentum equation, the Ampere's law, several densities, that is the total density, impurity density, neutral density, etc., the thermal energy equation, as well as an equation for the transport of runaways. So runaways are subjected to parallel advection or diffusion, and on top of it, they are subjected to the E cross B drift, as well as not only the avalanche source, but also other primary sources are included. So all these equations put together, 9 or 10 partial differential equations, these are solved using second order finite elements in the poloidal plane and Fourier decomposition in the toroidal direction. So after discretizing using implicit schemes, you will get a huge system of linear equations at every time step, which is solved using a preconditioned GM-res. So that is what goes in the background. So the code is fully parallelized using MPI and OpenMP. So coming back to this specific case of ITER, so what we start is with a 2D simulation. So on the left-hand side picture, what you see is the starting point, which is a 15 megaamp typical ITER free boundary equilibrium. So taking that equilibrium, it is subjected to something of an artificial thermal quench to drop the temperature from several hundred million to about 20 eV or so. So once the temperature is quenched, so we introduce neon and deuterium into the plasma as if it is injected, and also a small runaway seed that is introduced into the plasma. So since the plasma is cold and resistive, so you see that the total plasma current starts to decay, the runaway current starts to increase. At the same time, it is vertically unstable, and the plasma column, as you can see, is moving upward. So if we leave it like that, the whole thing simply becomes very small and the discharge ends. But what we do, we are interested in 3D dynamics here. So at some point of time, we switch to 3D. So what we really do here is switch to 3D when at a certain point when the Q95 is close to 2. Like I said, ITER will have a natural tendency to reduce Q95, and in such a case, after a certain movement of the plasma vertically, you see that Q95 drops, and at this stage we shift to a 3D simulation. So this is a plasma with roughly 9 megaamp of total plasma current, all of which is carried by the runaway electrons, and we have a neon content of the order of 10 power 20 particles per meter cube and a resistivity of the order of 10 power minus 4 ohm meter. So with this as the starting stage for 3D, we introduce a perturbation and see what happens. So what is observed is that the perturbation grows exponentially, and at the end of the linear phase in a baseline scenario, we have the 2-1 mode and a 6-4 double tearing mode that are mainly dominant. So and the main message from this is that once these modes grow, so finally, due to nonlinear activity, you see that the runaway current that is shown in dashed line here simply drops to a very small value. You started with 9 megampere and you are ending with something like around 350 kiloampere. So what is happening because of which the runaway beam is getting lost? We'll see that. So at the end of the linear phase, if you see at the top left-hand side picture, so you have the 2-1 tearing mode leading to stochastization of the magnetic field closer to the edge. So afterwards, the nonlinear activity is leading to further stochastization, and what is important here is the stochastic region keeps on growing and the core continues to shrink. So one of the main reasons that we observed for the core to shrink is basically that runaway electrons get lost from the stochastic region. Since they travel at speed of light, if the magnetic field becomes stochastic, then they get lost quickly. So there is a sharp gradient between the density of runaway electrons in the closed flux surfaces and in the stochastic region. So the color that you see is the density of the runaway electrons. So red means you have lot of runaways. So clearly you see that over the duration of the nonlinear phase, nearly most of the runaway electrons are lost. This is a good sign because this paves the way for benign termination, which means that as it is no more as a beam, it is getting spread out, so to say. Now we have also looked at plasma resistivity and its effect on this. Why is it important? So we are looking at stone cold plasmas here. So after a disruption, you have a plasma with impurities which due to impurity radiation reaches a temperature of the order of 2 to 3 eV or even less, sometimes even 1 eV. So this means the resistivity can be extremely high compared to the normal fusion plasma, and this can have a significant impact on the dynamics here. So we have tested what resistivity does for such a simulation, and what is observed is that at higher resistivity, background resistivity of the plasma, we see that the modes grow to much, not only is the growth rate larger, but the modes in fact grow and extract much more energy than the baseline case. And what is even interesting is that in the nonlinear phase, you see much more stronger stochastization and a near complete loss of relativistic electrons. So you see that in the bottom size picture, the 2-1 mode is far more dominant. The islands are much larger, the structures are larger, and this typically is seen as the fact that there are no other modes that are extracting energy, so that most of it is coming to the 2-1, when eventually you see that instead of 350 kiloampere, you have probably only a few tens of kiloampere left in the larger resistivity case. So this seems to be quite advantageous and is in fact good for ITER. Now coming finally to the wall loads. So we also looked at what is the actual final impact of this stochastization on the wall loads of runaway electrons on ITER. A 3D wall model of ITER is used, and from the simulation that we had, runaway particles are seeded and they are followed to see where they will end up on the wall. So what is observed in short is that at higher resistivity, you actually see that the area over which the loads of the runaway electrons are getting onto the wall is increasing significantly, and that means the spread of runaway electrons is much larger. But nevertheless, it is seen that even after all that, the area with a load that is greater than the beryllium limit of 18 megajoule per meter square, which is the melting limit for beryllium wall, is still anywhere between 0.1 to 1 meter square. That means it is still not something really foolproof, so to say. But this is in fact the first such simulations where we are able to show that in ITER benign terminations of runaway electrons can be executed. And more importantly, ITER has a natural tendency for that to happen. Now something very interesting is going on in the recent years in experiments. So what is observed is that, as I said, runaway electrons are sometimes leading to benign terminations. This is happening because a massive amount of deuterium is being injected from outside when you have a runaway beam. So what experimentalists observe is that when the plasma is significantly neutralized, that is when the ion or electron density is much lower in the background plasma, then it is leading to benign terminations as compared to a plasma that is not so ionized. So in this picture that you see, which refers to the Aztec subgrade experiments a couple of years ago, you see that at much lower densities, you are seeing a benign termination, that is the wall temperatures are much lower than what you observe at higher densities. So, and this is not just unique to Aztec subgrade, it is seen in a number of other devices as well. So this is then quite important in the context that this can be in fact a recipe. If we can understand this well, this can be used as a recipe for benign terminations in ITER, but also the dynamics on why this is happening is very less understood. So experimentalists and theorists have not much idea on why this is happening, but if they use this recipe, they are getting benign terminations. So we are currently trying to look at this problem with respect to the Aztec subgrade, and we start with 200 kiloamp limited plasma and do similar such simulations with free boundary treatment for the non-zero modes. So we are already observing some interesting differences between a plasma that is at 2 eV and a plasma that is at 1 eV. So I mean, in terms of ionization, you know that a 2 eV plasma is nearly fully ionized, whereas a 1 eV plasma is almost roughly say 2% ionized, say at 0.95 eV or so. And you see in the bottom picture that the loss of runaway electrons is far more for a low temperature plasma than a high temperature plasma. So while the investigations are ongoing, what is in fact key here is that not only the growth rates, that is if you have low ion density, alpine speeds are much higher, but not only linear growth rates, but even in the nonlinear phase, we are seeing that manifests in a way that the core is intact when the ionization is larger, but when you have the weakly ionized plasma, the core is also fully getting stochastized and the runaway electrons are efficiently lost. So these investigations are going on, and we'll have more exciting information going further. So finally, I'll quickly touch upon another interesting aspect which we are working is related to the plasma equilibrium in presence of runaway electrons. So to be very brief, so if you take the guiding drift orbits, guiding center drifts of runaway electrons, you have the usual E cross B drift, grad B drift, and the curvature drift. So the corresponding current density due to guiding center drifts also will have these three components here. So, but if you also look at the magnetization current, which is the current density component coming from the gyro motion, then you will see that the magnetization current comes out also to have three terms, where the grad B drift term simply will get cancelled out with what you had from the gyro guiding center motion, but the curvature drift will not cancel out because you have a P pop here as well, while you had a P parallel there. So this means that there is no exact cancellation of this magnetization current and gyro current. No, magnetization current and the guiding center motion current for runaway electrons. So what this means is that unlike a traditional plasma without relativistic electrons, the Grad-Shafranov equation, the classical version of the Grad-Shafranov equation is no more valid if you have a relativistic electron beam. So this means this J cross B is no more equal to equal to grad P. Grad P is anyway negligible in a cold plasma. So, but this curvature drift effect starts to become important. So what this really manifests as is also in a way known. So if you plot the flux surfaces for a relativistic beam plasma and the drift orbit surfaces, that is surfaces of constant canonical angular momentum, then you have a relative shift between both of them, and the shift is increases significantly with energy of runaway electrons. That means if you have low energy runaway electrons, then you tend to the limit of Grad-Shafranov, but if you have high energy relativistic electrons, then it won't work anymore. So what is important here is that when you get reconstruction, equilibrium reconstruction from experimentalists, it is very often that even abroad, these reconstructions are made without taking into account these shifts. So that means the initial equilibrium that you might start with is itself not so accurate. So what is relevant here is that these shifts can significantly alter the way modes grow and the plasma instabilities evolve. So this is something that we are looking at by including these effects in the MHD model that we have in Jurek. So with this, I would stop now and just have this slide over here.
Thanks, Vinod. Thanks, Vinod. So we can take only two questions.
Hi. Oh, thank you for the nice talk. I'm Subham from IPS Academy. So my question is, how are you considering MHD in your in your picture? Because I have two issues. One is you are considering the runaway electrons as a separate MHD flow, and the rest of the plasma as a MHD flow.
Yes.
So how are you considering the charge neutrality in this system? Secondly, I presume
how are they coupled?
Charge neutrality in this system.
Charge?
Neutrality. So initially you consider,
okay.
Charge neutral, then the runaway electron got separated. Second, related to the same question is that I presume the runaway electrons are non-thermal in nature. Non-thermal in nature. They are not Maxwellian distribution. They do not.
Yes.
So how do you incorporate these non-thermal electrons into MHD? Thank you.
Yeah. So to your first question, regarding charge neutrality, I mentioned that these runaway electrons, since they move at speed of light, you don't need a high density of them to carry the same amount of plasma current in the tokamak. That means the number density of runaway electrons are a factor of 1,000 or 10,000 smaller than the other thermal electrons that you have in the plasma. So this means that their contribution to charge neutrality is negligible. So your other question is about the fact that relativistic electrons will not be Maxwellian, will not obey a Maxwellian distribution. So doing a fluid model is wrong. That is in fact right. So we are not saying here that fluid model is a perfect model to study these, but it so happens that still in spite of using this fluid model, we are able to extract most of the features that are relevant to these problems. So, or in other words, we are not making any claims or comments about what it cannot do. We are only evolving the density of the relativistic electrons, which is very, very much legitimate to do. We are not commenting about the momentum space distribution.
Hello. Yeah. Hello, sir. I'm Vibhor from ISC Bangalore.
Yes.
I have a question that this runaway electron avalanche is a form of self-organized criticality.
Avalanche is not a self-organized current. So what happens there is you have a small population of electrons that are moving, that have relativistic energies. So if such an electron hits another electron at rest, say, then both of them will become relativistic. This is because the relativistic electron has far more energy or momentum than it is apparent from its velocity itself. After an electron reaches speed of light, it keeps on increasing its mass and momentum, isn't it? So that means it is able to convert another thermal electron into a relativistic electron.
Okay, thanks.
Thank you, Vinod, for a very nice talk. I actually want to draw a parallel with space plasmas. In the Earth's magnetosphere, you also have Van Allen radiation belts where you have relativistic electrons. There, the avalanche effects creates killer electrons which can affect the satellites. But now when these killer electrons interact with the ions there, it produces waves. So I'm sure that in your simulation, in the tokamak plasma, where you add ion impurities, it will generate waves. Have you quantified the amount of time the waves take to dissipate vis-a-vis your benign time for your killer electrons to kind of give away the energy to become benign? And how do this wave dissipation impact the temperature growth in the wall of your tokamaks?
We have not ourselves looked into these issues of waves affecting these runaway electrons. There are other groups studying aspects related to Whistler waves, etc. So I'm not an expert to comment on that.
Thank you.
Yeah, so this is again the problem of coupling with somebody asked
Yes.
from the past. So if you go to your equations, don't go, or if you look at your equations, there is an equation for runaway electrons.
Yes.
And then it's coupled only through the background electric field potential. There is only the only term is U term, right? Coupling the runaway electron density to the rest of the plasma.
Yes.
That's the only term, right?
Yes, so these runaway electrons come into Ohm's law. So in that way, it also comes into
There is no
Faraday's
psi
law.
term there, right? In
Pardon?
the runaway equation, there is no psi, magnetic stream function.
Yes,
term.
yes,
Is there?
yes.
Okay.
Because, as I said earlier, only the thermal electrons are subjected to resistivity. So if you have an electric field eta J term, so the J has to be only the thermal part of the current, not the whole current.
Okay, so if I want, I can apply a vertical field through that.
Yeah, you can. You have to use an eta J minus J runaways.
Okay, so thank you, Vinod.